started. So it's a pleasure to have today Dr. Adam Bergasser, who's an associate professor of physics at UC San Diego, and an observational astronomer interested in the atmospheres and evolution of the lowest mass stars, brown dwarfs, and extrasolar planets. Originally from Buffalo, New York, Dr. Bergasser earned his PhD from Caltech in 2001 with the thesis that introduced, I guess, a new class of brown dwarfs called P-spectral class. And then following postdoctoral appointments as a Hubble Fellow at UCLA, and a Spitzer Fellow at the American Museum of Natural History. He then went on to be a faculty member at MIT and then moved as a faculty member to UCSD. In addition to his astrophysics research, Dr. Bergasser also investigates physics education, both from active learning viewpoints and arts-based perspectives. I guess that's a nice picture. It makes quite show up.
This is not art.
Oh, okay. At least you have an eye for really nice pictures, I think. And he's also actively engaged in addressing issues of equity, diversity, and inclusion in the physical sciences. So probably some of you remember him from last August when he was at the Theory Boot Camp, talking about the UCSD astronomy program, the graduate program. He's also chaired the American Astronomical Society Committee on the Status of Minorities in Astronomy and co-director of the UCSD Morehouse-Spelman Pathways Program. It's a pleasure to have you talk about research.
Thank you very much. Is there a way to lower?
Yeah, I'll lower.
Okay. I don't have there's not a lot of pretty pictures in my field of research, so it's not too critical, but that's okay. So thank you very much. Thank you for the invitation to come here and speak on some of the work that I've been doing fairly recently. This is a collaboration with some colleagues at the IAC, which is the Institute for Astrofísica de Canarias. I was fortunate to spend 3 months in the Canary Islands, which is not too much worse than Southern California, but it's still pretty good. And work with a couple of collaborators there, both from Spain and also from Ukraine, on an interesting sort of project that binds, which I think is probably two of the very most disparate areas in astrophysics, the very origin of the universe and the stars that are closest to our sun. And you'll see what the connection is in just a moment. Oops, maybe not, because I'm at the end of my talk. There was it, okay. So before I start, I wanted to just do a quick advertisement. As was mentioned, I'm chair of the Committee of Status of Minorities in Astronomy. And one of the conferences that we're organizing coming up in June at Vanderbilt University is a conference on inclusive astronomy. And so sort of the best practices for making graduate programs, research programs as inclusive as possible. And I know that CSU LB is a hotbed for inclusivity. I'm really proud of the APS Bridge program that's here. And so for those of you who are interested in sort of how do we make our culture more equitable, this might be a great conference for you to attend. That's going to be happening in June. Okay, so what we talk about today is, again, this connection between the early universe and brown dwarfs that we've identified through one particular element, which is lithium. So I'll talk a little bit about lithium in the stellar and cosmological context, why it's such an important element, not just for understanding our origin of the universe, but also in terms of understanding how stars work. I'll talk about these terms brown dwarfs and L subdwarfs, which are the astronomical jargon of du jour today. And then I'll talk about the specific project, the pilot project that we did to sort of see how we could disentangle the lithium signatures in these objects and relate that to the cosmological context. And then I'll talk about some implications of that work and some next steps. So just as a super broad context, it's good to remember that lithium is on the periodic table. It's one of the light elements, one of the lightest metals in the periodic table. This is a hunk of lithium. In fact, you can't hold a hunk of lithium because it's extremely reactive in oxygen, and it makes a lithium hydroxide, which is actually this stuff right here. So if you have ever been very sad, or you have parents who've been very sad in the 1960s, my dad was on this substance for quite some time. That's lithium hydroxide. But lithium is actually now, what the most common use of lithium today is really in batteries and glazes in ceramics. About 50% of the lithium production worldwide is devoted to those two technologies. And of course, this is the technology that's coming up the most. Most of you probably have some lithium in your possession right now because of lithium batteries. And then lithium chloride, you might actually, if you dig up in your air conditioner, many of you who have older air conditioners might actually have some lithium chloride salt because it's one of the most water-absorbing salts that's known, and that keeps the air sort of nice and dry when you have air conditioners. So lithium has been used a lot in our sort of daily lives. So it's interesting to think about where lithium actually comes from, and probably the most astonishing fact that I actually hadn't realized up until the point where I did this project is that most of the lithium comes from the Big Bang. A large fraction of the lithium that we see here on Earth and around the universe was actually produced just a few seconds to minutes after the Big Bang in this period of Big Bang nucleosynthesis. This is a plot from a survey on the lithium problem, which I'll talk about in just a moment, by Fields 2011, but this is showing just one of sort of a traditional chain of nuclear reactions that's considered when you sort of predict what kind of elements come out of this very early period of the universe's history when the universe is very hot and it's capable of fusing sort of the basic protons and neutrons that are around at that early time. And so you get, you get deuterium, you get tritium, you get helium, you get a little bit of lithium, you get even less beryllium. There's some controversy about whether you get any boron or carbon or if that stuff completely decomposes before it gets a chance to really settle down. But these are really the trace species of the Big Bang, all right? The fraction of these light elements, lithium and deuterium and helium in particular, those fractions in either the interstellar medium or as we'll talk about in the very oldest stars in the galaxy, provide some measure of how well we actually understand the process of the Big Bang nucleosynthesis and perhaps our models of Big Bang in general. So in particular, lithium is a great tracer for this process. Now, this is where most of lithium was formed. Where does it go other than our batteries? Well, in fact, lithium, the biggest sink for lithium in our universe is the centers of stars. This is our PP chain, PP1 chain here, PP2 and PP3, right? Proton-proton chain. And this chain right here is the reaction that both creates and spontaneously then destroys lithium in the cores of stars. And incidentally, this reaction produces very high energy neutrinos. So this is actually also the source of the homestake neutrinos, the homestake experiment that measured the sort of neutrino rate from the sun, discovered neutrino oscillation. Those neutrinos are actually coming from this chain of the reaction. About 30% of all the energy coming from the proton-proton fusion in the sun comes out in this reaction right here. And so, like I said, it creates lithium through electron capture on beryllium, and then very quickly that lithium is destroyed through proton capture to form nice stable helium atoms. This process is extremely quick. This is actually a fairly slow process because of weak interaction. This is a very quick process. And so the actual amount of lithium in sort of equilibrium at the center of the sun is extremely tiny. And in fact, if you have any lithium in sort of the core parts of stars, almost all of that gets destroyed through this reaction very early on. And so if you were to sort of track the universal abundance of lithium over time, as stars begin to form in our universe and become more abundant, the overall universal lithium abundance starts to go down because of this. Now, stars are also probably a small, minor source of lithium as well. There are cosmic ray spallation reactions. So cosmic rays hitting the surfaces of stars sort of mediate the production of lithium and other light elements. There's some evidence that lithium may be produced in novae, not supernovae, but just novae, sort of just normal reactions off white dwarfs. These are kind of production processes that probably happen later in the evolution of the universe, sort of more recent times. We can see that in some of the evidence of lithium abundances. But for the most part, you can think of stars as the main sink of lithium. So, stars being the sink, we can also take stars and see what's happening to lithium over time and as a function of the properties of the stars themselves. There's been many studies that look at lithium because it turns out there's a really fantastic line of lithium that's in the optical, which I'll show in just a moment. But here are some of the general trends. When you look at stars of different temperatures, what you find is that some of the hottest stars, so stars basically hotter than the sun, you do see some traces of lithium in their photospheres. So this is plotting the lithium abundance, and I won't comment too much. There's sort of 3 different ways of reporting lithium abundances, and they all differ by some constant factor. But just think of this as sort of the baseline close to primordial abundance, but we'll talk about why there's a difference in just a moment. So hot stars tend to still have lithium in their photospheres. They're not destroyed in the core because those hot stars have a radiative boundary in their interiors, and lithium simply doesn't make it through that boundary to get destroyed in the cores. So you're sort of left over with whatever lithium that was formed in the atmosphere sort of remains in these very hot stars. But as you get to cool stars, you can see the lithium abundance drops down very precipitously. And that's because that lithium is churned down into the core through convection. Yes, sir?
Yeah, I just want to mention.
Yeah.
So the measurement of lithium is the same way as hydrogen. So there's a particular wavelength that there's a transition that you measure it that way, or how do you know there's a lithium on the surface?
So I'll actually talk about this because this is one of the sources of the lithium problem is how well do we actually know lithium once we measure it with one particular line, and I'll talk about that line in a moment.
Okay.
Yeah.
Just one initial question. So you mentioned about the radiative boundary. I know that there was some, or maybe it was a convective boundary in the case of the sun. There was some issue about where exactly it's located. And
Yeah.
so are these things, when was the sort of, like, do these numbers kind of move around over time? Or
Well, so this is just observational, right? So, this is purely based on the effective temperatures from the stars themselves, and the lithium abundance is measured through this one line, which we'll talk about in a moment. And you see this very sharp transition, and that's about the temperature you expect to see this transition where the convective boundary reaches the sort of temperature where you expect lithium to start to be fused. It's not exactly where the models predict, and one thing I mentioned in your office but not yet here is, in fact, even the sun, we don't fully understand why the sun's lithium abundance is so low. It's about 2 orders of magnitude less than the meteoritic abundances. If we understood stars fully, we would expect it to be fairly close to the meteoritic abundances because the convection boundary shouldn't be where lithium is fused. But actually, the sun is fairly highly depleted in lithium, so it seems that much of that lithium has been fused in the core somehow. So there are details which we'll talk about in just a moment. But just kind of broad strokes, hot stars tend to have lithium in their photospheres because it doesn't make it into the core. Cool stars don't have or have very little lithium in their atmospheres because that lithium does get down to the core, does get fused into helium, and basically disappears from the interior of the star. Now there's whole sorts of details in this that I don't have time to talk about. There are indications that the rotation rates of stars has an implication on lithium abundance, that there's some metallicity dependencies. You see that there's, for example, a gap here. There's sort of lots of lithium in these stars, and then there's a bunch of stars that have no lithium. These are all upper limits. So there are sort of other parameters that people are thinking about what happens to lithium in these atmospheres. We're mostly interested in the upper edge here, as we'll see in just a moment. And I'll just also mention that the idea that lithium can make it down into the core and slowly get burned away is seen in the ages of stars. And so this is, again, lithium abundance versus the ages of stars based on various empirical relations. And you can see there is kind of an envelope of maximum lithium abundance that as you go to later stages, it seems that lithium is being depleted. Although there's a huge scatter of both of these plots, many orders of magnitude in scatter. So there's a lot about the lithium problem that we don't fully understand. So if these stars at least seem to preserve lithium in their outer photosphere, if you want to get a measure of what the lithium was right after the Big Bang, looking at these hot stars, and particularly looking at very old hot stars, might be a way of actually getting a direct measurement of what the lithium abundance is when those stars form. And so this has been done for several decades now. One of the most famous papers is by Spite and Spite in 1982, where they looked at the lithium abundances of several hot stars, hot halo stars, so stars that are in the halo part of the galaxy. They have orbits that indicate that they weren't formed in disk, or they were scattered at such large orbits because they've been around for so long. These are the oldest stars that we know of in our galaxy. When they looked at the lithium abundance of those stars, what they found is that they were fairly constant and relatively independent of metallicity. So total metallicity is down here, and this is again a measure of the lithium abundance. And you can see most of these triangles here are falling at roughly the same value within a few tenths of a dex. There's a slight increase here, which has to again do with the cosmic ray spallation addition of lithium in the photospheres. But the fact that the lithium abundance doesn't change over this very broad range of metallicity, and you can think of this as also a measure of age. So the very oldest stars will have the lowest metallicities. The very newest stars will have metallicities that are more close to solar. The fact that it was fairly age independent and metallicity dependent was sort of confirmational that the lithium is really coming from the Big Bang, right? You make all these other elements, iron, titanium, carbon, oxygen, inside stars, but if the lithium is mostly coming from the Big Bang itself, the abundance of that element shouldn't change, right? As long as it's not being depleted inside stars. So at least that fit the picture. The problem was this decrement of about half a dex, and that may not seem like a lot in astronomy, but our understanding of what this Big Bang nucleosynthetic lithium abundance is, and actually now informed by the WMAP experiments, has a fairly strong constraint on what lithium abundance you'd expect to see right after the Big Bang. So it's somewhere around 6 times 10 to the minus 10 lithium atoms per hydrogen atom. Right? This is a number. But all of the stars that have been observed here have much lower and significantly lower lithium abundances. This is about a 5 sigma discrepancy. And so this has, in fact, this discrepancy has grown over time as we get better measurements. It doesn't get better, it gets worse. And so this has become known as the lithium problem. And it's been one of the big outstanding issues in terms of understanding what is actually happening in the Big Bang nucleosynthesis. So there's a bunch of solutions that have been proposed for this problem. It could just be a stellar problem in the sense that we really don't understand stars well enough. We don't really know what happens in their interiors. Maybe lithium is mixed deeper than we expect it to be. Maybe the line that we use, which is a neutral lithium line, actually, lithium is a light element, so a lot of the lithium is actually ionized. So you're only getting a trace measure of the lithium abundance. So it may be that we don't fully understand the degree of ionization, and we're just underestimating the amount of lithium in their stars. Right? These are seemingly kind of trivial issues, although of course they touch on our basic understanding of stars. There could be bigger problems. Perhaps we don't understand the nuclear physics as well as we thought we did. Perhaps there are problems in the assumptions made in the Big Bang nucleosynthesis. Perhaps there are reactions that we're not including in that nucleosynthetic chain. And there's also, when you've taken your stellar astrophysics course, you know that there are around certain energies, there are resonances and nuclear reaction rates. Perhaps we're missing some of the resonances because we're not able to sort of simulate those at low energies in our reactors. And it could even be a bigger problem. Perhaps this is a post-standard model problem. Perhaps there's something like dark matter decay processes or even dark matter catalytic processes where dark matter actually facilitates some reactions that may play a role in the amount of lithium abundance, at least early on in the Big Bang nucleosynthetic era. And then there are folks that have proposed that perhaps you can just have these changing fundamental parameters. There have been these sort of iffy, suggestive results that perhaps things like the fine structure constant have changed since the beginning of the universe. If you change, for example, the deuterium binding energy by just a little bit, you can actually resolve this discrepancy. Of course, that means you have to change a fundamental parameter of physics, which seems like a fairly extreme solution to the problem. So, I'm going to assume that, in fact, it's more likely to be a stellar problem. And so we can ask, is there a way that we can actually prove that it's a stellar problem? And, for example, can we get rid of the stellar problems, or at least the problems that we think stars invoke? And one way to do this is that if ionization is a problem, maybe we don't want to look at hot stars. And if it's the mixing or some process that's actually destroying lithium through fusion, getting lithium down to the fusion regions, if we could find cool stars that don't fuse lithium, all those problems go away. Which would mean if we measured lithium in those stars, we could actually tell whether the lithium problem is a star problem or if it's something more serious. So that's kind of the premise of this experiment. So I'm going to switch tacks now and talk a little bit about what these cool stars might be that don't fuse lithium. And those cool stars are the brown dwarfs. These are a class of objects that kind of bridge the regime of stars and planets. If you kind of think about this historically, we've separated out stars and planets for about 10 or 12,000 years now. All right, stars are the things that are fixed in the sky. Planets are things that were moving. Up until about, say, 200 years ago, that was good enough for most everyone else. Of course, then we realized that planets are things orbiting around the sun, but they were still different, right? Even when exoplanets were found, those were still things that were orbiting stars. They were not stars themselves. It's really the discovery of these objects that sort of indicate that there's really more of a continuum of mass, a continuum of properties, radiuses, also atmospheric properties that I'll talk about in just a moment, where actually stars and planets are kind of on the extreme of this now continuous spectrum as opposed to in different places. So depending on what grants that you're applying for, you might consider these to be failed stars because we see them in stellar environments, and they're failed because they don't fuse hydrogen. We'll talk about why that's in a second. If you're getting NASA money, of course, you want to call them super Jupiters. And the reason is that because they cool over time, and I'll talk about it in a moment, they do achieve the same atmospheric temperatures, compositions, and even spectra of many of the planets that we're spending a lot of resources to get a measurement of, and I can just point at a brown dwarf and get a spectrum just like that pretty quickly. So, this is one of the reasons where it branches. Now, they were predicted actually quite a long time ago, back in the 1960s. In fact, just a little over 50 years ago, last year, in sort of a theoretical mind experiment. So. Keep in mind when stars are forming, they really start off as very large molecular balls of gas and dust. And it's that contraction of those gas balls into something that's more like the size of the sun liberates a lot of heat from gravitational potential energy. That heat is enough to trigger those fusion reactions, and now you've got a self-supporting star. If you start with less mass, you've got to shrink that thing down even smaller to get out the same amount of heat. And so the question that folks like Shiv Kumar and Hayashi Nakano in Japan asked is, well, how small do I have to shrink this thing down? Is there a limit to how small the star can be? Can I take this pen, and shrink it down to the equivalent size and start fusing protons inside a pen? It doesn't work because you have to shrink this smaller than a proton, which means you can't really fuse protons on. So there's clearly some fundamental limit to how small you can make a star. And what they found was that limit was really the point where you run into degeneracy pressure. So this is a plot showing the core density versus the core temperature. These lines are showing the evolution of their models. So they take, again, a very large star, low density, low temperature, let it collapse down so it gets more dense and more hot. At some point, it crosses the point where instead of having thermal pressure supporting this collapsing star, you actually run into the point where you have degeneracy pressure, electron degeneracy pressure, as being the main pressure support. And once you hit that point, right, the star essentially stops collapsing, which means it's not getting any more energy from the gravitational collapse, which means it's not getting hotter anymore. And you end up kind of in a dead end, right? A star that's supported not, again, by thermal pressure, by the pressure of the fermions being too close together, they can't get any closer, and they can't cool off any further. They're basically at the point where they're at their maximum density. And so if you hit this point before you reach this critical threshold temperature, which for hydrogen is somewhere around 3 million degrees, you essentially never are able to fuse hydrogen. You never get hot enough to do that. And so you end up with a ball of hydrogen that's extremely dense, but is not fusing hydrogen. Right? It's not acting like a star. It's literally failed stars. Now, this is a great, sort of theoretical idea, and that's all it was for about 30 years. It wasn't until the 1990s that the first example of this was found. Today we know there are thousands of these things that we know about just near the sun. And in fact, it may be that these things are among the most numerous objects in the galaxy. Estimates for the number ratio of brown dwarfs to stars in our galaxy goes anywhere from 20% all the way up to there being 50% more brown dwarfs than stars. This is a very uncertain number because, in fact, most of these brown dwarfs are so cool we probably can't see them. But that's actually exciting when you find this whole new population you've never seen before. Yes?
Why did it take so long to find them, and now that we have thousands of them?
Yeah, so I'll talk about their cooling in just a moment, but the main reason is because they don't have this source of energy in their cores, their surfaces just radiate all their heat away. So they become these very cold objects, 1,000 Kelvin, 500 Kelvin. The coldest one we've seen so far is about 300 Kelvin, which is, this temperature, right? So they're essentially invisible in the optical. They're getting to the point where they're invisible even in the near infrared. So they're infrared sources. And it took until the 1990s when we had sort of large enough infrared detectors, sensitive enough infrared detectors that we could put on telescopes that we would start seeing these things in abundance. And now that we have lots of surveys, we have lots of brown dwarfs. Yeah. Okay, so touching on the temperature thing, so one of the amazing things from that lack of fusion is that these are not static objects. They are not in equilibrium, thermal equilibrium at all. So if you take a normal star, a star may be relatively cool, so these are kind of the lowest temperature stars that are known, but eventually reaches a point where the energy that's being radiated from the surface, which we see with our eyes, is the same amount of energy as being produced by nuclear fusion in the core. So this is a thermally stable object. But these objects don't have that source, and so over time, so this is time in a sort of log scale, in effective temperature of the surface, these brown dwarfs just steadily cool and cool as they get older, right? Down to really cold temperatures, right? 500,000 degrees, they can get even cooler than this. Just depends how long you want to wait. So we classify these things now based on whether they evolve. So stars will get to an equilibrium point, and these particularly very low mass stars will essentially last for many, many, many times the Hubble age of the universe. But brown dwarfs are steadily cooling. We even have things now that people are calling planets because we don't actually really know what to call them. These are objects that are so low mass that not only do they not fuse hydrogen, but they also don't fuse deuterium either. So these are elements these are stars that don't fuse anything. Deuterium is sort of the easiest thing to fuse in the stars. These don't fuse anything. So maybe they're planets, maybe they're not. This is a contentious word. I'm not going to get into it. So this is an interesting point because that means that brown dwarfs actually evolve. So this is a little movie I put together. This is the same evolutionary plot, temperature versus time. And then this is a sort of series of models that are sampled at the temperatures that this model here is going to track. So these are all different masses coming along here.
So the question,
Yeah.
do all brown dwarfs fuse deuterium? I know for Jupiter, our Jupiter, for example, there was some discussion that the extra heat could be due to some deuterium fusion on the core or something. So, but is that for all brown dwarfs or some category?
So the standard model of you know, isotropic gas ball that's in sort of some kind of pressure thermal support, that the minimum mass you'd need to get hot enough to fuse deuterium at the core is about 13 times the mass of Jupiter. So as long as it's more than 13 times the mass of Jupiter, the assumption is that those things have fused deuterium. And that should say that deuterium fusion happens very quickly, very early on. The deuterium abundance is very low. And so, so it doesn't actually make that much difference in the evolution, except actually you can see these little humps right here. That's the deuterium main sequence. And that lasts for less than 50 million years. So it's a minor part of the evolution of the star. But these things are probably too low mass, although that's still just model dependent. All right, so so just watching our little bouncy ball go here, you can see how the spectrum changes over time. I've talked mostly about the interiors, but in fact, the most dramatic changes are happening at what we can actually see from the surface of the stars. As these things get cooler, you get these increasingly complex spectra. And the reason they're so complex is because they're becoming more like planetary spectra. Most of the features you see here are molecular features from things like water, methane, ammonia, carbon monoxide, and that makes a very non-black body spectrum, right? And indeed, it makes it something that looks a lot more like a planetary spectrum. So that was models. This is real data showing 3 of the classes of brown dwarfs that we know today: the M dwarfs, the L dwarfs, a T dwarf, and this is in fact Jupiter. So actually the spectrum of a planet. And you can see there's not really that much difference between this coldest class that I have here and the spectrum of Jupiter. And the reason, of course, is that it's the same absorbing molecules, predominantly methane in this case. And again, very distinct from black bodies. These look a little bit like black bodies, but you can start to see some molecular bands from water coming in. But all these are starting to look a lot more messy, all right, a lot more like planetary astronomy. And then today we've now actually identified 4 classes of brown dwarfs. The M dwarfs are just the coolest stars. We've known about them since Secchi first did the first classifications in the 19th century. But these 3 classes of stars, the L dwarfs, T dwarfs, and Y dwarfs, have only been discovered in the last 20 or 30 years. As mentioned, that this was actually part of my thesis, but the L dwarfs were discovered not too soon after that, and Y dwarfs were just discovered in this actually last few years now. And these are sort of the basic temperatures that they span and some of their basic atmospheric properties. And I'll point to the L dwarfs because we talk about that most of all. These things are really interesting because they're reaching the temperatures where you actually don't just have gas in the atmosphere, you actually start to condense out solid things. And if you think about what's the hardest stuff to melt, that tends to be things like rocks and metals. That's the stuff that's condensing out in these atmospheres. So we're looking at clouds of dirt and clouds of molten iron. It's terrible weather, all right? Especially from Southern California. But it makes lots of really interesting atmospheric properties and stuff, which I won't have time to talk about, but it'll be something that we may touch on a little bit later. All right, and then these things are things that we're still trying to understand a little bit more.
So there's
Yeah.
raining rocks.
Raining rocks, yeah. It's actually raining gems too. Actually, they're mineral gems. The main condensate in L dwarfs is actually aluminum calcium oxide, which is perovskite. And perovskite's the main element with some tracers of rubies, sapphires, and padmarachas. So it's, you know, there's a mining opportunity here. Speak to me later. All right, so we go back to this evolutionary plot where I divided up in terms of how they evolved. Those spectral types are really based on their temperatures, and so this is where they lie on this chart. So the M dwarfs are kind of up here, mostly stars, but some younger brown dwarfs. The L dwarfs are really interesting because the very oldest ones will be stars, these will be brown dwarfs, and these might be planets. And then you've got planets and brown dwarfs and T dwarfs, and then a bunch of other stuff down here in Y dwarfs. So if I focus in this a little bit, because this will be relevant for what we talk about next, if I just take one particular subtype within the L dwarfs, say L4, which is actually the subtype we'll be talking about a little bit later. That's all I know is its spectral type. I actually don't know a lot about this star because if I don't know its age, it could either be a planet that's very young. So this might be the age of, for example, some of the very nearest young association stars that we have near our sun. It could just be a plain old boring brown dwarf at about 500 million years. Or it could be a really old thing that's actually a star, that's actually cooled off to the point where it's thermal emission is just balancing the very feeble amount of fusion that it's producing in this core. Right? That threshold for hydrogen burning is not a sharp threshold. It's kind of a gradual decline. So if you get a star that's just cold enough, you could actually take literally 5 billion years to reach the main sequence. And then you got a star. It took a long time, but you're there. Okay? So just knowing the spectrum type isn't actually enough. We need more information to determine whether what we're looking at is a star or a brown dwarf or a planet. Right? Because there's funding right there. All right, so what's one way we can do this? Well, we can go back to lithium, right? That was the whole point of this talk, and go back to this reaction. So as I mentioned, in low mass stars, fully convective stars, you don't see any lithium because any lithium that was in the star has been convected down into the core and has been just eaten up by lithium, these reactions, right? This reaction right here. But there's a threshold temperature for each of these reactions, and so this is just rough, but at sort of the given sort of pressures of the interiors of stars, as I mentioned, hydrogen burns at about 3 million degrees, deuterium at about 1 million degrees, and lithium is kind of in between at about 2.5 million degrees. And so in fact, if you rank these, the hydrogen burning temperature is the greatest of these, deuterium is less, and these correspond to the masses at which those elements should be fusing in the cores of their stars, again, based on sort of our current star formation models. And so this is the limit for brown dwarfs, about 7% of the mass of the sun. Above that, you have hydrogen fusion. Below that, you don't. But just a little bit less than that, about 6.5% the mass of the sun. Above that, you can fuse lithium. Below that, you don't. So remember, part of the goal was to see if we can identify things that don't fuse lithium. And we can do that if we can find objects that are below this mass. Because no matter what's happening in those interiors, however much mixing is going on, how much atomic diffusion, how many gravity waves are propagating, no matter where the lithium goes inside the star, it's not going to get hot enough to fuse. So whatever lithium you start off with, you're just going to keep. That's sort of the golden goal here. Now, historically, this lithium temperature has been very important. In fact, some of the first brown dwarfs that were found by the detection of lithium. So here's the line that I mentioned earlier. This is the line at 670 nanometers, which is actually covered by this plot here. It's the lowest level transition. It's actually a doublet line, and it's a neutral atomic line. But it's very easy to see in the optical spectra. There's really sort of nothing else in the sort of absorbing region around this line. So it's very obvious to detect. And the very first discoveries back in the 1990s were the detection of lithium, of this lithium feature in some very cool stars. Again, which shouldn't be there because cool stars are fully convective. All the lithium should go down to the bottom and get burned away. But the fact that lithium was still here meant that even if it was going down there, it wasn't being burned. This thing was too cool, so it had to be brown dwarf. All right, so that's the lithium test for substellarity. Another thing that happens is that even if you're not at that low of a mass, it still takes some time to get lithium down into the core, right? There's a finite convective mixing time. And it turns out that that time scale is somewhere between 20 and 200 million years. And so even if you have stars that are more massive than 0.06, 0.065 solar masses, if you're young enough age, you might still see lithium in their atmospheres. So not only is this a good test for brown dwarfs, it's also a good test for age dating stars. If you know you have, for example, a 1/10 of a solar mass star, but it has lithium, that means it has to be a pretty young star because all the lithium hasn't actually gone down to the core yet. So this fact has been used in a number of studies to age date different clusters. So what I'm plotting here is the temperature of stars in a given cluster, which is named here, versus, again, their lithium abundance. Again, these stars will retain lithium because they have this radiative boundary. The lithium doesn't make it past that. These stars are burning their lithium because it's being mixed down, but then you have this recovery at cool enough temperatures where the lithium comes back up. At very cool temperatures, these are just brown dwarfs, but here you actually have low mass stars, and it's simply that they haven't had enough time to burn all that lithium away. So this is known as the lithium age dating technique or the lithium burning technique, and you can see it provides some fairly accurate measures, at least in terms of our understanding of the nuclear physics of these particularly young clusters. Right? So that's a very common technique. Yeah.
So each part is that a one specific brown dwarf or the one object?
No, these are lots of stars in each of these clusters as a function of temperature. So so this one, for example, is labeled. This is PPL15. This was actually one of the first brown dwarfs found, and it actually has a little bit of lithium depletion in it. So it may actually be So there's a little bit of space between the hydrogen burning limit and lithium burning limit. So you can have some brown dwarfs that have fused lithium, but most of them haven't. So these are all brown dwarfs here. This is right on the border. And then these are all stars that have fused all their lithium away. But the things that are kind of right on the border there, they could actually be above the hydrogen burning limit, or at least the lithium burning limit. But they just haven't had time to deplete all those elements. You can see, for example, that this edge moves over as we go down, and those are progressively younger ages.
So that's the cluster.
That's the whole cluster. So these are all members of that cluster. Okay. So you can also use this for individual binaries as well. So if you've got two stars and you know they probably formed at the same time and maybe they straddle this sort of burning limit, you could use them to sort of fix the age. These are actually two objects, two L dwarfs, which don't show any lithium. And that actually provides a limit, a lower limit on the ages of those systems. So there's all sorts of tricks you can do with lithium around this very low mass range. Because, again, at a certain mass, it has to be fused. But that takes a little time. So at young ages, you can use that clock. At old ages, you can use just the mass cutoff and get an idea of the time. Now, as we go down in cooler temperatures, the fraction of, actually, I'm going to go back here and show this again. As we go down to cooler and cooler temperatures, the fraction of objects which are brown dwarfs goes up, right? You're not getting any of those stellar lines down here. And so you should expect the lithium abundance would keep going up as you go down in spectral type. And indeed, it does. This is a plot of the fraction of dwarfs that show lithium in absorption. You can see it's going up almost up to 80, 90% over here. But then it starts to drop at the end here. And so the question is, these all should be brown dwarfs. They're all so cold. There's no way a star can be this cold. So why do we start seeing lithium drop off? Well, it turns out that lithium has one more trick up its sleeve, and that it doesn't always have to be atomic. This is a pressure-temperature plot, which is very common for chemistry calculations. So pressure on the bottom here, temperature going up, and actually decreasing as we go up, because we'll see why in a minute. And these shaded regions are different forms of lithium. So down here you have atomic lithium in dark, and then this sort of gray region is lithium chloride, lithium hydroxide, and lithium fluoride. These are all just the favored states of lithium at these particular temperatures and pressures. This yellow band is the photosphere of a given star, the part you actually see, right? Somewhere around a 0.5 in terms of bars of pressure, log 0.5. And these are the pressure temperature profiles, what the pressures and temperatures are as you're stepping through the star. So where these lines intersect the yellow band is essentially what you see, and essentially the chemicals that you see in the atmosphere. And you can see for the L dwarfs, you're fully solidly in the sort of atomic lithium range. But this T dwarf, which is going to be cooler for a given pressure, because it's a cooler star, you're actually in the range where lithium is in either lithium hydroxide or lithium chloride, or even up here, it's in solid lithium fluoride salts. So the L dwarfs are great for the lithium line. As we go too cold, in fact, you start to lose that line, not because it's burned, not because lithium is burned, but because it's chemically depleted. It actually starts to form molecules like within the atmosphere here. So there's a finite range where we can use this. All right, so let me go back to the original problem. Remember that we were trying to see if there's a way that we can measure whether this offset here is actually a stellar problem or some other bigger problem. And we wanted to look and see if there were L dwarfs, or at least cool stars, which don't fuse lithium. Cool so they don't have the ionization problem, don't fuse lithium so you don't have to worry about the interior stuff. And if we can measure the lithium abundances in those, then maybe we can see if that agrees with the Big Bang Nucleosynthesis, and that would tell us it's a stellar problem. If it doesn't agree, it means there's something else going on. So that's the goal. All right, so that was the experiment we did. I'll just point out that there are L dwarfs in the halo, L-type brown dwarfs in the halo. Spectra will probably be a little mysterious for you to read, but the black line here is one of these L subdwarfs. The red line is just a normal L dwarf. And these differences that you see are because that L subdwarf has fewer metals in its atmosphere. Remember I mentioned early on that a star that has much fewer metals probably formed early enough in the galaxy's history where there weren't as many metals around. They hadn't been formed by other stars yet. So the fact that we see these stars have fewer metals in their atmosphere, and when we look at their kinematics, in fact, their galactic orbits are all over the place. This is the galactic orbit plot. This is sort of the range of the bulge These are the spiral arms. We're about here, and this star is not going in a nice circle around the galaxy. It's actually going in a backward circle around the galaxy. It's a retrograde star. So these are clearly not things that form nearby in the disk. So we know these things exist. There's something like 15 of them known. And so our goal was say, okay, these are the best cases right there. They're cool, right? L dwarfs we know can be brown dwarfs. And we know these are halo objects. They're very old objects. So these are the things we want to look for lithium in. So we targeted 2 sources, both SD, subdwarf, L, mid-type Ls, both relatively nearby. This is about 50 parsecs, 34 parsecs. These are pretty close by stars. Both very low temperatures that we can infer from their spectra. We spent about 6 hours using the VLT on 1 star. And we spent about 4 hours using the GTC. This is the Gran Telescopio Canarias, which is actually the largest optical telescope in the world, sad to say, for Keck. But we had an instrument on there called Osiris that we used. And again, we have to spend lots of time on these objects in order to get enough signal noise because they're so cool that that region around the 670 lithium line is very, very faint, very little continuum. So we have to literally stare at these objects for hours just to get enough light to see if we can see the line. This is what the spectra look like. I'm not going to go in detail. There's a lot of features in there. We can actually use these data to measure the radial velocities of the stars very accurately. And when we do that, we get the galactic orbit. So I showed this one earlier, this kind of funny star. This is actually my favorite. So I do this a lot, collecting galactic orbits, because we find a lot of these weird moving stars. This is probably the most interesting one I've seen. This star is going in a nice circular orbit, but it's actually going around the pole of the galaxy. I've never actually seen a star do this before. So it essentially has no angular momentum because it's going straight in, but it's actually going around the galaxy like this. Most stars go around this way. This is going around this way. And so the art picture I showed earlier was imagine 50 million years in the future and you're riding along with this sort. You'd actually get this beautiful view of the top of the galaxy. It'd be wonderful. You should start selling tickets now. All right, so that's kind of all fun and games. What about the actual lithium? Well, here is the region around that 670 line. This is now shown in terms of relative velocity, so it gives you sort of an idea of how broad our spectra are. And these dashed lines show where the lithium line should be based on uncertainties and wavelength calibration. And you know, there's something kind of there in this spectrum. There's really nothing there in that spectrum. These are definitely not detections of lithium like the kind that we would see in these other stars. And in fact, just to drive it home, this is this spectrum right here compared to a series of different atmosphere models where all we've done is change the lithium abundance. So the red line has the sort of typical kind of lithium abundance we see in nearby stars, and then it gets stepped down by factors of 10. And at some point, you don't notice the differences anymore. The blue lines are the same. That's why we chose blue. Because you actually are confusion limited at that point. Now, we usually think of confusion limited when you got lots of stars and you can't figure out which star is your star. This is, we got lots of lines. We can't figure out what line is our line. All of this stuff, this is a model. This is not noise. Those are just a forest of mostly calcium hydride, but also titanium oxide lines. And we literally can't separate out those lines from this atomic line that we're looking for, right? We're in a forest of absorption. And so that sort of sets our limit to how sensitive of a lithium line we can see to something like 10 to the 3 less than that in the sun. Now that's still pretty small. And in fact, it's so small, if we go back to sort of more robust units looking at the number of lithium atoms and hydrogen atoms, we can set a limit that's about -11.5 in log units. And keep in mind that the BBN predictions are something like 2 orders of magnitude higher than that. So these are not primordial lithium abundances. In fact, I would say there's probably no lithium in these stars. And these are stars. They're burning lithium. And they fully can mix that lithium into their cores. So we simply haven't gone cold enough, right? We've gone in the L dwarf regime, but these are not cold enough stars to actually be not stars, to be brown dwarfs where they're not using lithium. So we need to find cooler objects. Now I show this plot. This is from an earlier paper that I wrote looking at the optical spectra. We were looking at these kind of objects. There is one more source that's cooler than this, that's nearby the sun. It's only about 20 parsecs away. And it's definitely cooler. It's about 250 Kelvin cooler than these stars. And this is something we're going to try to do in the next sort of observing cycle. We've asked for 8 hours of Keck time to do this because that's the only way we can do this. If this doesn't work, we're SOL. And we are definitely SOL because if we were to go in the T-dwarf regimes, remember I mentioned that the lithium abundance is dropping down at the end of the L sequence because of this chemical depletion. It's forming lithium chlorides and hydroxides. Just last year, we found the first T-type halo brown dwarf. The problem is this is 5 magnitudes even fainter than this one, right? 8 hours, 100 times fainter, right? We can't do this, right? It's completely out of the question. Now, it may be that we could look for the molecular features. Those are out in the infrared. No one has ever seen these before in any of the sources we've looked at so far. You require, again, very, very sensitive mid-infrared spectroscopy. So we may have to wait for JVS T if we're going to do this in the T-dwarf regime. So I actually think this is our best last shot. If it doesn't work, then it didn't work. That's okay.
Okay. The molecules, they try to look for them.
Yeah, so when Spitzer IRS was still functioning, there were a couple programs to try to look for the particularly lithium chloride feature. And the problem is it's right on the edge of the IRS short low band, which goes out to about 15 microns. This is somewhere like 17 microns. And so the next band over is much lower sensitivity. And in fact, there's really been no usable data at that long wavelength part of the Spitzer IRS that's come out from groundwork programs. These are just really faint stars. It's just very hard to do this set at the kind of sensitivity we need to. So that's, like everyone, we've got to wait for GTC. Okay, so I'll summarize what I talked about. So I want to sort of emphasize that lithium is, again, one of the most important elements in sort of understanding not just stars and brown dwarfs, but also sort of making this connection with sort of our early universe. It's definitely present in most of the brown dwarf elements, atmospheres that we see, and it's present at the abundances in which it's formed. None of this lithium gets processed, right? It doesn't get burned. And it's fully mixed inside the stars. And so whatever you see at the atmosphere is really the abundance of the entire interior. And so when we make measurements of lithium abundance, we're actually making measurements of what the lithium abundance was wherever the star was born. And we can do that today with just the normal field L dwarfs that are fairly young. But that's not getting us at the primordial abundances. And so if we could do the halo brown dwarfs, we could actually maybe make a measure of primordial abundance and test whether this problem between the Big Bang Nucleosynthesis predictions and the actual observations is a stellar problem or something that's a lot more serious. And we tried a pilot study and didn't detect anything, and that just means that they're stars, but we may have another chance. It's like our last great hope, right? And it may be we have to go even colder, but this is going to lead to all sorts of other problems because we won't probably see atomic lithium. We're going to be seeing other stuff, and it's a much, much more difficult problem. So keep your eyes glued on this particular element. I think there's going to be some other results coming out on sort of other normal type L dwarfs. But I think this is a really interesting sort of connection between these sort of two different scales of astrophysics, even if it didn't work this time. All right, thank you very much.
Thanks for that. So I think I can echo that. It's a very outstanding problem in astrophysics. Working very hard to do. So it's another great effort. So questions?
You mentioned the James Webb Space Telescope.
Yeah.
Is that going to happen in your lifetime?
Yeah, well, I mean, it should. It should be happening in like 2-3 years or something like that. Hopefully that's in my lifetime. But, you know, these are big projects, right? So, you know, there's always the, you know.
I might not work.
Well, I'm not even going to like jinx it in that way. But, you know, the biggest problem is always that any kind of these big projects, it's like, you know, it's going to be a year out and then the delay time is 1 year per year. So we'll see. I think it's probably, I'm hopeful it'll come out in 2017. It's probably gonna be closer to 2020. But, you know, the other thing is that everyone is waiting for GTC for everything. So whether this problem merits enough time, we'll see.
Can you say if you were to understand helium and beryllium really well, then we don't have to worry about lithium essentially.
Well, no, but that's the problem, is that the deuterium abundances, the helium abundances are smack on.
So those are understood very well.
Yeah. Well, so there's always a danger you get the right answer, but you don't know why, right? So the deuterium predictions, deuterium measurements, and I think the helium-3 predictions, the helium-3 measurements are basically right on. It's only the lithium that's off. And it's really only lithium 7 because lithium 6 is, so another isotope lithium 6 is much lower abundance, so it's very hard to get those measurements. But lithium 7 is the only element that's really way off. And that's why, you know, people think this is probably a stellar problem, because if it was really we don't understand nuclear physics, we don't understand our modern physics, all the other ones should be off in some way as well. But it's really just lithium. So that's why it's a interesting problem.
Wait, can you take this down to the level of, say, super Jupiter?
Well, sure. I mean, because at least young superjupiters will have the same temperatures as the L dwarfs. And I showed the. I'll actually go back real quick here. Let's do. Right. So I showed this plot that if you're a 20 million year old planet, we'll call that a superjupiter, right? If you're young enough, you can be in the temperature range where you'd be in an L dwarf class, and you might expect to see lithium to be there because just chemically it should be there. And we do see systems like this. We see free floating systems like this, so it's questionable whether they call it superdupers or not. We see, for example, the HR 8789 planets are actually even cooler than this. So we're actually directly detecting those planets and this sort of temperature regime. Now, so it's possible to detect lithium around those. And that's a perfectly valid investigation. It won't really tell us much about the primordial lithium because those objects have formed pretty recently. So they're reflecting the abundances today. And if we really want to know what the abundances were sometime after the Big Bang Nucleosynthesis, then the oldest stars are the ones we want to target. And actually, that's the problem, is that, you know, if I wait enough time, these lines keep going down. So if I'm really pushing it past 10 million years, it's hard to be in that range, in a very narrow part of the mass space. So, we'll see.
How long do you actually need to look at it?
Oh, I don't know at all. Actually, I haven't done any calculations to figure that out. Yeah, I wouldn't even want to hazard a guess. It would be short or long, something like that. That's my guess.
Any more questions? So I know you're focused on the stellar solution, but
Yeah.
You know, how much do we know, say, about all the experiments that we do for fusion reactions, for example? That we do in the lab and we kind of push them down. There's resonances and extrapolations and things. So
Yeah, I mean,
if your physics problem, do you have some sense of, like, you know, that be as could a small change there maybe get your model kind of work, but just a tweak in the nuclear physics maybe somewhere?
so, and this is mostly reflective of my ignorance of the laboratory experiments, but I haven't really seen many experiments focusing on lithium, in part because you have to collect enough of it. And the reaction, well, I have that as the next thing. You know, this reaction still requires 2.5 million degrees. And so, you know, this is kind of a fusion plant experiment, and I haven't seen any results from that. Now, there is this, the laser work that Lawrence Livermore lab has been doing. I don't know if they've been doing specific experiments in Livermore. There's also the Z machine, and I don't know if they've been doing experiments specifically. So there may be something on that, but I haven't actually looked into it myself.
Any last questions?
Just could you perhaps take a mnemonic hydrogen atom and bombard it with an atom with it get close enough to a fusion experiment?
I wouldn't even know. I mostly look up, so I don't look down. I mean, I think you're still getting into the very small, small number of reaction rates issue. So you really want to pin down the resonance, profile. I'm not sure how long of an experiment that would have to be in order to get that done. And I don't know to what degree that would necessarily, because if you're doing muon catalyzed experiments, then you have to be probing muon catalyzed experiments inside the stars. And this is a fairly, this is not a weird reaction in any way. So I think this would dominate without any muon catalysis. So I'm not sure if you might throw off your calculations for what the resonance rates would be if you're using muon catalyst. But again, I'm not as familiar with the laboratory experiments as I am with the astrophysics.
So you have chosen, I mean, your goal was to explain the deficiency.
Yeah.
Then from your data, you didn't see any lithium in the
No.
object you're looking at.
No.
What does that mean?
No, it just means they're stars, right? So if they were, so you know, our measurements are somewhere down here, right? They're depleted. They've had lithium fusion, and that lithium has mixed down into the core. So essentially, we didn't find an object that we could actually do the experiment on. And we don't know. The problem is we don't know a priori because, again, all we know is the spectral type of the star. We don't a priori know what the mass is or what the age is, and so we kind of have to just make a measurement and see if we've gone low enough. And the result is we did not. We have one more, like I said, star that might be cool enough, but it may also be too high mass. It may still be above the lithium ring, in which case there's no stars to do this with, which would be sad, but that's big. There's a little uncertainty when I talk about the chemical depletion. Those calculations I showed were for solar metallicity abundance mix. If you reduce all of the metal abundances by a factor of 100, it may change the chemistry enough that, you know, for example, lithium hydroxide, lithium chloride, you need to have enough chloride to form it. So it may be that the lithium preserves in its atomic form at a much cooler temperature if you get rid of all the other elements. And that's actually something we really think might happen because the lithium abundance is not going down. Lithium comes from the Big Bang Nucleosynthesis, so its abundance is always somewhere around here. Everything else might be very, very low. So if there's now less chlorine and less oxygen, you're just not going to form as many of those molecular bands. And you'll just have plenty of extra atomic lithium around. And we're hoping that's the case, but we'll worry about that when we get there.
I guess in like comments and things like that, or grains, they have anything useful to say about this problem, or it's all sort of, that's all compounds, I guess.
Yeah, so I mean, lithium is still present in you know, you can still measure lithium in meteoric samples, but it's mostly integrated into various salts and minerals, mostly minerals.
So if there's no more questions, let's thank Adam again.